here. This week, we're only going to be doing what is called optimization problems, where we use our calculus to find the optimization of some objects. But before we do that, I want to go over this problem. It seemed like last week you were struggling with some of the derivative graphs, okay? So I want to go through this problem and I want to talk about derivative graphs. There's a difference between a derivative graph and a normal graph. And I'm gonna go to a clean sheet of paper. Yes, and that is one of those things where you know it's coming on the AP test. There is no question about it. Okay, so let's say I gave you just a regular function, and we call this the f of x graph, but that's not the graph they usually give you. Okay, so I'm just going to graph this out. I'm going to make new graphs here, just so we have something to look at. And I always go back to things that I know, and that's why I do this graph here. Okay, so if I did the graph of y is equal to x squared, okay, I know that. I know what that graph looks like. It looks like this. Okay, so this is y is equal to x squared. I'm going to recall this. I'm going to call this f of x equals x squared. Okay, then I know that f prime of x, well, the derivative of x squared is 2x, right? So I know that the derivative graph is going to look like this. So this is what the derivative graph looks like. It just goes up, and that's the derivative graph. Now, this is where I think you were getting confused. This is the graph that they want you to think about. This is what they give you. They give you the derivative graph, and they want you to be able to explain what's happening on the f of x graph. So if I take a look at this derivative graph, wherever it crosses the x-axis, there has to be a max or min. Anything below the x-axis, the original graph is decreasing. And you can look at that. From negative infinity to 0, this graph is, I'm going to say that f of x is decreasing. Well, if you look at f of x, it's sure enough, it is decreasing. It's going down, 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 down until it hits 0, and then it starts going up. So everything below the x-axis, so anytime you have a derivative graph, anything below the x-axis, the original function is decreasing. Every time you have something above the x-axis, the original graph is increasing, and you can see that. So now if you have a function that decreases then increases, this is a minimum value at 0. So you can look at the original graph and it's like, oh yeah, there is a minimum value there. So that's what they're trying to do, is they're trying to they always give you the derivative graph, and then they ask you things about the original f of x graph. And you don't, I mean, obviously you don't get to see this. You only get to see this. And how do you find points of inflection? Well, points of inflection are where the slopes change. Well, the slope is never changing here. It's always positive on the derivative graph, so there's no points of inflection. And if it is a positive slope, that means it's concave up. Well, this has a positive slope everywhere. Well, guess what? Look at this original function. It's always concave up. So those are the things that when you look at a derivative graph, you have to be able to, tell what the original graph is doing at those points. Okay, so let's go back to my files here. Let me see here. I need week 17. Okay, so let me turn this one off and turn this one on. Okay, so in this problem, okay, this is a AP exam problem that was on, I'm not even sure what year it was on. On what intervals, if any, is f, okay, so this is f prime. So they're asking, where is f increasing, okay? So what would you say, where would f be increasing on this, for this problem? -3 to -2, that's absolutely correct. So part B, it says find the x coordinate. Yep, because it's above the x-axis. That is absolutely right, and that's what you would put. On part B, it says find the x-coordinate of each point of inflection and then justify your answer. Okay, so where are the points of inflection? X equals 0, x equals 2. That is absolutely correct. Why? Because the slope is changing, and this is, and because when you find points of inflection, that's second derivative. So we have the first derivative, so second derivative is the slope. Well, where the slope is changing, that is a point of inflection. It's changing here, point of inflection. It's changing here, point of inflection. Okay, so that's absolutely correct at x equals 0 and x equals 2. And then the last one, it says find an equation for the tangent line of the graph of f at 0.03. Okay, so they gave us a point. The only thing we really need is the slope at there. I don't even care about that because that one you didn't have a problem with. It's just the slope or the increasing, decreasing in points of inflection. That's what I was worried about. Okay, so now the next 2 weeks, week 17, which is this week, we're going to talk about optimization problems. Don't think you'll have any problems with them. And then week number 18 is the semester exam. Now, you can take the semester exam anytime you want. It is set up very similar to what an AP test will look like. It has 4 sections. It has a multiple choice part, it has a free response part, with calculator, without calculator. So that is the next 2 weeks. So next week we don't have, no, there is only 1 attempt on the exam. So be very careful. Now, I'm not going to count the exam for very much. If you had all advances, the exam is not going to take you down. The exam is just to get you ready for the AP test, just to see what it looks like. Do I want you guys to do well on it? Sure, but it definitely is not going to change your grades. Okay. So don't worry about it. Just try to do your best that you can. All right, so this week we're going to talk about optimization problems, okay? Optimization with calculus. While today's graphing technology makes it easy to find extreme without calculus, the algebraic methods of differentiation were understandably more practical and certainly more accurate when graphs had to be rendered by hand. And back in the olden days, trying to find an optimization problem, you really had to use calculus. And nowadays, we could just graph it out and we'd find the answer. But here are the strategies that we want to use this week, okay, for solving a max or min problem. Number 1, understand the problem. Read the problem carefully, identify the information you need to solve the problem. Develop a mathematical model of the problem. I always draw a picture of what I'm trying to find, what I'm trying to maximize or minimize. Number 3, graph the function. Find the domain of the function. Determine what values of the variable make sense in the problem. I rarely will graph the function out. I'm just going to use calculus to solve. But a lot of times the numbers don't come out real nice. So we do have to put it into our calculator and find out where it crosses x-axis. Identify the critical points and endpoints. Solve the mathematical model and interpret the solution. Okay, so that's the way our book tells us to solve these problems. Let's try an example. So here's an example. It says an open, and this is a very, these are types of problems that you'll see a lot of. It says an open top box is to be made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides, as in the figure. How large should the squares be made, or how should the squares be to make the box hold as much as possible? So what we're trying to do is we're trying to maximize the volume here. Okay. Now, when I used to teach face-to-face, I used to hand out a sheet of paper. I don't think I did a 20 by 25 piece of paper, but let's just say I did. Okay. Let's say I gave you a piece of 20 by 25 inch piece of paper. And what happens here is you always want to write your equation in one variable. you do not want to use an x and a y because it makes it a whole lot harder to solve, okay? So we're going to say that this side is 20 and this side is 25. Okay. Let's say I cut out a 1-inch corner here. For every thing, it was just 1 inch. I just cut out a 1-inch square here. So what is the dimensions of this piece of paper now? Okay, so I cut out a 1-inch square. So volume is equal to, let's say, length times width times height. Okay, so in this problem, what is the length? What is the width? What is the height? If I cut out a 1-inch square there, okay, what would the length be? What would the width be? Let's start with the height. What is the height of the box if I cut out 1-inch squares? 1 inch, right? The height is just 1 inch because that would go right here. It would just be 1. Okay, what would the length be? 18. Okay, that would be length or width, either one. It doesn't really matter. And what would the width be? 23. Okay, so now, oops, 23. So if I wanted to find the volume of that box, I would just go volume is equal to 18 times 23 times 1. And I'm going to get out my trusty calculator here. 18 times 23 times 1. And I end up with a volume of 414. Okay? Now, they want us to maximize the volume of this box. So let's try 2-inch height. Okay? So length, width, height. So I'm going to try 2-inch height. Okay? So I'm going to put 2 here. So I'm going to cut out 2-inch corners. So what would the length be now if I cut out 2-inch corners? 16. What would the width be? 21. Okay, now if I multiply that together, all right, so I've got 16 times 21 times 2, I get 672. So obviously, if I use these dimensions, I get a much better volume. There's more, this box holds more water or whatever it is that they're putting into this metal container. So now what we have to do is we have to find a generic formula that we're going to take a derivative of to find the absolute maximum here. Okay, so I'm going to go volume is equal to, I'm going to let H be X. That is going to, the amount of paper that or the amount of, I'm going to cut out, that's going to be X. So that's my height. Okay, so how would you find the length? If you know that the height is X, how do you find the length? Using X as one of your variables. Well, if you take a look over here, the original piece of paper or whatever it was 20 inches. So that would be 20 minus 2x. And then what would my width be? It would be 25 minus 2x. So now I have a crazy formula, but this is a formula with one variable. Okay, I'm going to write this down because I'm going to erase what's on there because it's going to take a little bit more work to finish this problem off. So volume is equal to x, 20 minus 2x, 25 minus 2x. Okay, so do you see how I came up with that formula? All right, so I'm going to erase this. And then I'm going to make my pen a little bit thinner so it doesn't take up so much room when I write. I'm going to use red here so it sticks out more. All right, so my volume is equal to x, 20 minus 2x times 25 minus 2x. Okay, so I don't want to take a derivative of this. This would be crazy to take a derivative of this. So what I'm going to do is I'm going to multiply this through. So if I multiply the x through, I end up with 20x minus 2x squared times 25 minus 2x. Okay, so I wanted to get that together. Now I'm going to do FOIL. I'm going to just multiply this out. And that is going to give me 500. Is that right? Doesn't sound right. Well, I guess it is. 500 x minus 40x squared. And I'm going to multiply this way. Minus 50x squared plus 4x to the third. If I add this together, so I'm going to write it in standard form, 4x to the third minus 90x squared plus 500x, and that's what volume is equal to. So basically what I did is I just rewrote the thing, so now when I take a derivative, it's super simple, right? If I had to take a derivative of this, it's going to take me a while because I'm going to have to use the product rule 2 times. Now all I have to do is take the derivative with respect to each term, so it's much easier. So volume, the derivative is going to be 12x squared minus 180x plus 500. Since I'm trying to find the derivative set equal to 0, correct? This is where it gets a little bit confusing because there is no way I'm going to be able to find where this is going to be equal to x. It's not going to factor. So what's one method that you can think of that we could solve this using technology? I'm going to turn on my second here. Not right. Not what you wrote. I'm trying to get my Desmos calculator up here. See if that works. Get rid of that, and that. Okay, so graphing, right? And wherever it crosses the x-axis, those are our solutions, right? So before we go on here, can you tell me what x cannot be larger than? I mean, x could be 1, 2, 3, 4, 5. What is the largest value x could be? Because remember, you're cutting corners out of there. Could you cut a corner that is 7 by 7? I disagree with you. The paper, the shortest side of the paper is 20 inches, right? So I could cut a 7 by 7 out. I would still have 4 inches left. Well, I'd still have 6 inches left, right? What if I cut out, could I cut out 10 by 10? Because if I cut out and that's where, you'd cut out 10 inches here, and you'd cut out 10 inches here, there's nothing left. So 10 inches, we know that our answer can't be more than 10, okay? So x has to be less than 10. There's no way it could be more. I don't have enough paper to cut out, or tin, or whatever it is. And it can't be negative, right? So now I'm going to go to my sharing application screens. I'm going to go to my Desmos calculator. And what I'm going to do, and I hope you can see this. Can you see my Desmos calculator now? Okay. So what I'm going to do now is I'm just going to plug in my equation. It was y is equal to 12x squared minus 18x plus 500, I believe it was, plus 500. Uh-oh. I must have made a mistake someplace because I don't see that graph anywhere. All right, let me go back and see what I did wrong here, because that does not I thought it was 180x, not 18. 180x. Okay, let me put that in there because that, so 180x. Okay, all right. So that cross, because I know it has to cross between here. So I'm looking at this, and it looks like my solution is 3.68, 3.681, and it crosses at 11.39. Well, I know 11 can't be part of my solution, right? The reason it can't be part of the solution is because I can't cut that big of a square out. It doesn't make any sense. I don't have that much material to cut that much out. So I know my answer has to be the did I say 3.68? It seemed like it was more than that. All right, let me go back. Leave here. Oh no, I just left. Okay. I'm going to get rid of this. Go back to 17. Okay. Was that 3.618? Okay. So that means I can find out what the length, width, and height would be, because the height, let me put that on there. So h is equal to, make that a little bit thinner there. H is equal to 3.68. That means the length would be 20 minus 3.68. So let's see here. So 20 minus 2 times 3.68, 3.68, and that gives me 12.64. And the width is going to be 25 minus 2 times, what was that, 3.68. And that gives me 17.64. So now, if I wanted to find the total volume, that gives me the largest total volume. I'm just going to multiply 3.68 times 12.64 times 17.64. And hopefully I get more than what our last one, I think 600 and something was the largest that we had. So 3.68 times 12.64 times 17.64. And I come up with a total volume of 820.52. Now, do you see why businesses would like this? I mean, the first one that we did, we came up with like 200 for volume, that the box could only hold like 200 cubic inches of whatever it was doing. Now I've made my box so big that I can hold almost 4 times that amount. Now I can hold 820.52. Using calculus, I was able to maximize the volume of that box. Does that make sense? All right, let's try a couple examples. So let's, there's a garden one that I think is, this one is very, you're gonna get one just like this tonight. There's no question. There's always one open container box and all that kind of stuff. Let's see here. I want to take a look here. I want to see if I have a garden one, because that one is pretty cool. That one works pretty well. All right. Okay. So here's a garden problem. Okay. So here's a garden problem, and I want you to try this. It's very similar to the one that we just did. Okay. It says a farmer plans to fence a rectangular pasture adjacent to a river. Okay. So this is a river here. So you don't need fence here. Okay. This is a river. You do not need fence. Okay. Let's see here. The pasture must contain 720 square meters in order to provide enough grass for the herd. No fencing is needed along the river. What dimensions will require the least amount of fencing? Okay, so you're gonna have 700 or 720,000 square meters in order to provide enough grass. What's the least amount of fencing? Okay, I'm going to let you try this, and you might not get very far because we've only done one problem so far. Give it a shot, see what you get, and then we will go over it. All right, let's take a look at this. Okay, so the first thing I do is I always ask myself, okay, what did they give me? Why did they give it to me? So they gave me that this is going to hold 720 square meters, okay? Well, so I'm just going to write that down. 720,000 square meters. How do you find area of a rectangle? Isn't it just x times y is equal to, and we know it's going to be 72,000. Now, I always want to make sure that I'm always dealing with one variable. So what I did in this problem is I just said, okay, I don't know if I want to deal with x or y. It makes no difference to me. Let's deal with x. So I'm going to divide through by y here. So x is equal to 720,000 over y. So wherever I see x, I'm going to put 720,000 over y. So now I have one variable. I have it in everything in y. So area, which is 720,000, is equal to this times this, right? Because length times width, or width times whatever you want to call it. So this is going to be y times, that doesn't seem right. Because it looks like the y's are just going to cross off. That, what did I mess up here? Oh, because I need to know. All right. Because this is going to be y, and this is going to be y. Oh, I need the perimeter. Yeah. Well, we're really doing perimeter, right? Because we want to know what we're trying to do is we're trying to get the least amount of perimeter. So this is going to be my x value. So what do I need if I'm trying to minimize perimeter? I'm not trying to minimize area. I'm trying to minimize perimeter, correct? So perimeter is going to equal y plus y plus okay. So if I rewrite this, I know my perimeter, I'm just going to use P, is equal to 2y plus over y. Okay, now, because when I was thinking about it, I'm like, oh, this is area. But the area formula helped me get this length as a y value. But then it's like, okay, I'm trying to minimize the amount of fence I'm using. Well, that's perimeter. I want to have the least amount of perimeter that I can, because that'll give me what I'm looking for. So now I'm going to take the derivative here. So the derivative of perimeter is equal to, what is that going to be? 2 plus, okay, and this is going to be, I'm going to bring the y up here, bring that down. So that's going to be I'm not going to have enough room here. So the derivative is going to be 2 plus negative 720,000 y. Oh, I'm taking it. And so that's going to be, boy, I'm not looking at this right because I'm trying to take a derivative. So we add, I was just working with BC calculus, so we're taking integrals or antiderivatives, which is going backwards. So derivatives, we subtract one off. So so this would be 1. So that would be just 2. And if I have negative 1 here and subtract 1, that's going to be y to the second, right? Y to the negative second. So that's going to end up being, so my perimeter is going to be 2 minus 720,000 over y squared. Did I take the derivative correctly there? That's why you'll see what I'm talking about next semester when we start taking antiderivatives, because one of them you add one to the exponent and one of them you subtract one. And when we take a derivative, we subtract one. When we take an antiderivative, we add one. So it is kind of confusing when you're doing both of them at the same time. Okay, so now I want to solve this. So I'm just gonna bring this over to the other side. So this is just going to be let's see here. So I bring that 2 over. So the derivative, because I'm going to set it equal to 0, bring the 2 over. So that's going to be 2 is equal to 720,000 over y squared. Bring the y squared up. So I'm left with 2 y squared is equal to 720,000. And I'm going to divide through by 2. This is going to give me y squared is equal to, is that 360,000? Then I'm going to take the square root of both sides. So y is equal to, is that 60,000? No, the square root is at 600. So 3,600. So the square root of, so it's going to be 600. So that means this is going to be 600. This is going to be 600. And this is going to be 7,200 over 600, so 720,000 over 600, which gives me 1,200. So these are my dimensions that will give me the area of 720,000, but it will also give me the least amount of fencing that I have to use there. And if you're a farmer, you're really trying to cut back on costs, so this would give you the thing. So they're kind of complicated, a little bit of complication in there, but trying to maximize, you want to set the problems up. So let's try another problem here. Let's see here. I want to see what I have here. Okay, let's see this one. All right, so this is a problem off of tonight's assessment. It says engineers are designing a box-shaped aquarium with a square bottom and an open top. The aquarium must hold 500 feet cubed of water. What dimension should they use to create an acceptable aquarium with the least amount of glass? So they're going to build this aquarium out of glass. It has to hold 500 cubic feet of water. What is the least amount of glass that they have to use? Okay, I'm going to let you try this one, and then we will try it together, or we'll work it through together, see what we get for an answer. All right. 44.72 and 60 or 6.687. All right. Now, I don't know. I haven't done the problem. I don't know if I have the, nope, I didn't put the answer key in there. Okay. So the one thing about this problem is that it has a square bottom. All right. Now, wait 1 second. Let me see if your answer just makes sense. How do I do that? I just multiply 44.726 is the 44, is that your height or is that one of the bases? The height? Okay. So then that's times 6.687, 6.687 times 6.687. And that gives us almost, that would be, that would give you a volume of 2,000, not 500. So I would say the answer is not correct. All right. So in this problem, the thing said that it has a square bottom. Okay. So that's kind of a little trick that they throw in there. So it has a square bottom. So that means I'm going to use this as X and this is X. Okay. Yeah. I kind of got to learn how to draw a little bit better. Okay. So this is, so then I've got, so this is going to be my, oh. That's a pretty bad aquarium. All right. All right, there's my aquarium. So if this side is X, this side is X, and I don't know what this side is, but I do know that they want the volume to be 500, right? So I'm going to put 500 for volume. So that is equal to X times Y, right? Or height. Let's just put H in there. Or I could write this as 500 is equal to X, 500 is equal to X squared times H, okay? But I don't want to use H in my problem. Okay, I don't. So this is my height. I don't want to use H in there. So I'm going to rewrite this. So H is equal to 500 over X squared. So in place of H, I'm going to put 500 over X squared because that basically is my height now. So I have X times 500 over X squared. Now that does not make sense because that X squared is going to cross out that X squared. That, no. All right, what did I mess up here? H, so that is H, X squared, because it's a square base here. Oh, there we go. There we go. All right, so again, I'm trying to, all right. So I needed to use volume to get the height here. Thank you very much. So what I need to do is I need to find the surface area. All right, so surface area is going to be X squared, right? That's going to be one of my sides, plus 4 times, and then all of the rest of the sides are going to be exactly the same, aren't they? They're all going to be 500 over X squared times X, right? If I'm thinking about this right. So I'm going to have 4 of those sides. So I really have 5 sides. I have the base and then the 4 sides, which would be X times 500 over X squared. Does that make sense? Does that look a little better now that I'm doing surface area instead of area? Okay, so then I'm going to cross out one of these X's, right? So I'm left with surface area is equal to X squared plus, what is that, 2,000 over X? So now, so did you end up with this when you took your derivative, the X squared plus 200 over X? Okay, so now if I take the derivative, I'm going to end up with 2x plus, what is that going to be, negative 2,000 over X squared. Is that right? I think that's right for my derivative. And then I need to set it equal to 0 because that's where you're going to get your max or min. So this is going to, and I'll write it up here. So I've got 2x equals 2,000 over x squared. So if I put the x squared up here, I get 2. X to the third is equal to 2,000. Divide through by 2, I get x to the third is equal to 1,000. So now if I take the third root of 1,000, okay, so x equals the third root of 1,000, which is, I need my trusty calculator out here for that because I don't know what that is. So that's raised to the 1/3 power. Oh, it's just 10. Yeah, 10 times 10 times 10 is 1,000. So that's 10. All right. So now I have, for my base, I have 10. I have 10. And I have 500 over 10 squared. Well, 10 squared is 100. So that would, the height would be 5. So my dimensions would be 5. That would be the height. And then the base would be 10 by 10. Does that give me 500 feet of water, a volume of 500 feet? And the answer is yes, it does. So I'm going to stick with this as my answer. Just calculation. Did you take the derivative incorrectly? Or did you solve for when you set it equal to 0? Oh, all right. That's as bad as me not knowing that the cube root of 1,000 is, is 10. All right. All right. So one more problem, and I think this problem was, oh, I know this problem was on the your assessment. I think this one is, I think this one might be also. And then this one here, it says find the length and width of a rectangle that has a perimeter of 40 meters and a maximum area. Okay, so why don't you try that one? My dog is scratching at the door, so I'm going to let him in. Give that one a shot and see what you get. I would have to agree with you. I wouldn't have even had to do any work on this one. because I know maximum area is always something closest to a square. That is always going to be your maximum area, as close as to a square as you can possibly get. So if I was going to do this problem, and I'll do the math on this problem. So we have a perimeter of that equals 40. So if I had to draw this out, I would go x and y, x and y. So I know perimeter is 2x plus 2y is equal to 40. Then I really want to get it into one variable, so I might just say 2x equals 40 over 2y, which really is 2x equals 20 over y. Oh, that's 20 over y. Okay, so that would be x equals. So now I know what x equals, and so I could put in place of this, I could put 20 over y, and in place of this, I could put 20 over y. Now, it wants a maximum area. So area is equal to length times width. So I would have, now I'm going to run into the same problem I have on every one of these. Oh, no. All right, so perimeter is y, so 40, 2x. You had 20 minus w. 2x plus 2y is equal to 40. Oh, because I'm using two variables to try to get to there. Yes, you're absolutely right, because if this was y and this is y, then we would just subtract it from 20 and 20 minus w. You're absolutely correct. Sorry about that. I'm not thinking today clearly. So then we would end up with w, or x, is equal to, as we take the area, we'd end up with w times 20 minus w, take derivative, and we should end up with w is equal to 10. And so that would mean this is equal to 10. This would be equal to 10. This would be equal to 10. And this would be equal to 10. So the whole perimeter is equal to 40, and it has the largest area there is. So you're absolutely correct. Sorry. My mind is just not working today. All right. So that is called optimization problems. What you want to do is you just want to set the problems up and then solve them. After you take derivative, set it equal to 0, and you should be able to come up with the maximum or minimum area, perimeter, volume. It really doesn't make a difference what you're doing. Whew, that is it for this semester. Next week is the exam. Now, if you finish this week's work and you want to start on the exam, you are more than welcome to do that. The exams are open. As soon as you're done with the first semester exam, you are done for the semester. And then you can relax until second semester begins. All right. Have a great week and try to stay warm. It is awfully cold out there. Bye.